All right, so good afternoon. Oh, wait, good afternoon. Okay, look, we've got some excellent panelists here, and we really want to engage you, so we need a little enthusiasm here, because I think we've got a really interesting topic. I think we're going to learn a lot together about this. Let's start at the beginning. So how many of you are familiar with quantum? That is, how many of you know them? Oh, good, okay, so that's pretty good. That's pretty good, great. It's good to know. We weren't really sure what the familiarity would be. So for those of you who are familiar, you know that some of the early experiments were like in the late 1800s, right, Heinrich Hertz. And then, let's see, Max Planck in 1900 did some theoretical work, right? But the thing that was interesting about quantum is that even the practitioners, they didn't quite get it, right? They didn't quite get it. So one of the problems with quantum is it's probabilistic in nature, right? Meaning that if you look at quantum, nature becomes random in some sense. So how many of you know what Einstein said about that? Einstein said he does not believe God plays dice. So even though he was one of the initial proponents of quantum, he has some questions about it. Another fundamental property of quantum is something called entanglement. How many of you have heard about some of the work recently in teleportation, that people have talked about teleportation? That's all about entanglement. But what did Einstein say about entanglement? He called it spooky action at a distance. So these pioneers all had questions about understanding this. What's really interesting about quantum is that it's one of the most rigorously tested fields of physics of any. It gave us lasers, it gave us all kinds of different capabilities. But it's very hard to understand really what's going on here. So what we'd like to do in this talk, because many of you have had some experience, many of you didn't raise your hands, we're going to start up in the beginning. We're going to talk about what is quantum, why is this interesting. There's three major areas where quantum is being used. It's quantum computing, quantum sensing, and quantum communications. We'll be talking a little bit about the first two, that is computing and sensing. Then we'll talk about applications, like why do you care about this? And then we'll go on a little bit further and talk about what are the other things going on right now, like education, for example, right? And at the very end, we'll start musing about what the future of quantum is and some research directions. So to get right into it, these are great panelists. I'd like our panelists to introduce themselves. After you.
Thank you, Reggie. So my name is Prachi, Vakharia. I wear a couple of hats. Today I'm representing WISER. So WISER is the largest quantum training program in the world. We train over 50,000 students across the world so far, 120 different countries. We receive a government grant, which is from the Department of Commerce, to really focus on the Elevate region, which is in the Mountain West in Colorado. But of course, we support the country nationally. Beyond the education side, we focus on research. So a lot of organizations come to us and ask us, well, where do we start with quantum? One of our most recent partners is actually a company called Vanguard. I think everybody knows the investment bank there. And one of the key questions they've asked is, look, we've had our AI people try to get them trained up in quantum. They still don't know what to do here. How could we use quantum for the finance sector? So those are the kind of questions we help answer.
Allison.
Good morning, everybody. Thank you to HSDF for having us and having this important topic discussion today. I'm Allison Schwartz. I'm the head of global government relations for D-Wave. It's a quantum computing company that is the computer, cloud access, full stack, hardware, software, professional services. We have both quantum annealers and gate model systems. We announced an acquisition today, and that's important because different problems need different types of compute. Annealers are best for optimization, and gate models, you'll need it for anti-corrosive materials and quantum chemistry and personalized medicine, but we'll get into that in the application side.
Thanks, Allison. So Allison, I'm going to start with you.
Sure.
So you talk with a lot of people, right, in your business. And I'm sure when you talk to people, you say quantum, some people's eyes open up, like, what is that, right? So how do you what's the simple story, like, what is quantum, and why should they care about it?
Sure. So I will first start with, I am not a quantum physicist. I'm a political scientist, and I came to quantum policy through fintech. So quantum is a different type of compute, especially from a quantum compute perspective. We are able to not just look at things, a regular computer looks at ones and zeros as the bits. Qubits can look at 1, 0, both, neither, all at the same time. My 11-year-old son says quantum is a mother's brain, because I say yes, no, maybe, all at the same time. But it allows us to look at a much wider variety of problem sets and provide an answer back. I will be the first person to say not all problems need quantum. Quantum is not going to replace high-performance compute. There is a synergistic relationship with classical compute, high-performance compute, AI, and quantum. And we can get into that afterwards.
Perfect. Prachi, many of you have probably seen cats when you talk about quantum. Why have people seen cats with quantum?
Have you all seen the cats, like why Schrodinger's cat? People have heard of Schrodinger's cat, yeah. So for quantum, really, it's a state of superposition. Is a cat alive or dead? This is an experiment that Schrodinger had, where he literally put a cat in a box, or theoretically put a cat in a box, I'm told, put a radioactive decayer, and if the radioactive decayer does decay, then it activates a poison, and the poison then gets eaten by the cat dies. But we don't know we don't know of the state of the cat at all until the box is opened. So this is the problem of superposition, and this is something that's beautiful in the quantum sector, is at some point it's 0 and 1, or it's 0 and 1 at the same time, or it's neither.
Mm-hmm.
So that gets to kind of the problem here, right? You got fundamental properties of quantum, superposition, entanglement, randomness. These are some of the fundamental properties that we all try to exploit when we're trying to use this to do useful things. And that's why it gets complicated. So let's get to what's the current state? And I'm going to leave to whoever wants to start here. What's the current state of the practice, and what kind of capabilities do you see us having right now?
Yeah, I can give you a baseline understanding of quantum computers themselves. Quantum computers, the research has been going for the last decade. We call this the second revolution of quantum. The first one gave us some things like MRI machines, for example, OLED TV screens. But this is the second revolution where we are tapping into and getting better at tapping into these properties of entanglement and superposition. And there's this whole race towards quantum computers, and there are different modalities that can hopefully get us there. So different groups are trying different things. One is a superconducting computer that requires fairly low temperatures, in fact, temperatures that are even lower than what you would find in space, for example. I have some friends at NIST, and something that they're developing works at 40 millikelvins, which again is much colder than space, 40 millikelvins. And this is why if you ever see a quantum computer, typically it's represented not by the box that it's in, but actually something called a dilution refrigerator, which is this golden chandelier that comes down. So that is a machine that it's golden because gold has a high conductive metal, and it's able to then cool the qubits itself, the device at the very tip, using helium that's pumped into it. But how we represent quantum computers is through then the golden chandelier. There are other methods as well. Photonics is a big one as well. I'm sure, like with photonics as well, and trapped ions, for example. If anyone tells you quantum computers are here in the next 3 years, 5 years, or 20 years, don't believe them. I don't think anyone really knows the answer.
Some of them are here and there are problems that can be solved today.
Yes, and that leads me to D-Wave of, well, how can we get started today?
Yeah, there you go. So again, I mentioned two different types. There's annealing quantum computers and gate model quantum computers. Each of them have different capabilities. Each of them are advancing on different timelines. So let's start with the annealer. The annealer is what D-Wave has first started to commercialize, and we actually have in production applications today. We are currently optimizing NTT Docomo's telecommunications network by 15%. We are currently optimizing automobile manufacturing. So for the defense industrial base, if you want to start to manufacture things better, faster, whatever you need to, there are manufacturing applications. Those are hybrid applications. So it is a hybrid solver that breaks it down, and the part of the problem that's too difficult for classical goes to the quantum processing unit. The gate model systems, which are more deterministic versus probabilistic, those are for quantum chemistry. Those are much farther away. There are a lot of errors that happen. Qubits are fragile. And so you need to figure out, detect the error, mitigate the error. D-Wave just acquired a company that has a technology that does error detection in real time through dual rail technology based out of Connecticut. So a lot of these systems are available in the cloud today. So for folks saying, how do I get started today and what is the state of play? It's cloud access. There are some organizations that are purchasing systems, but for the most part, it's cloud access. And one of the most important things is the skills needed for algorithm development are things that, and I know we're going to talk about skills in a bit, are things that can be developed today. And so that's kind of the state of play, is understanding what are the right problems. Quantum doesn't solve everything. quantum will never solve everything, no matter how big it gets. But once you get these larger quantum systems, both on the gate and the annealer side, you'll be able to solve a whole host of problems that are currently either outside the scope of today's classical, or you could solve them faster, and in certain applications that's important.
So what are some problems right now? You mentioned some optimization stuff around automobiles, right? What are some other problems that quantum annealing can solve?
So think of everything as an optimization problem, and let's be honest, when you look at national security, it's one big logistics optimization problem. So there have been applications, for example, for workforce scheduling for airport security staff. That is a huge problem. That takes way too much time to calculate the staff. And when folks were calling in sick, and especially during the pandemic, you had people who had to then quarantine for 14 days, but you had to have all of these parameters of you need certain females and males, and you need certain people with different types of backgrounds in each of the lanes. That adds on the complexity that quantum annealing can solve. And we've actually worked with some folks to develop prototypes for that. So think of it from an optimization problem, but you can also turn things into an optimization problem. We have optimized some modeling for LLMs. So the modeling of an AI that is taking forever and running and running and running, you can turn that into an optimization problem for some of them. And we've been able to do that so it's energy efficient. You heard in the video, energy efficient compute. It allows you to do that modeling much more energy efficiently, get the model better, and then you can deploy it through classical means.
Thank you for that.
Yeah.
Prachi, what do you think are some of the other problems that quantum can solve? Because that's particularly what, some of the D-wave problems it can solve. What are some other problems it can solve?
Yeah, think of other examples, and here I'll switch the topic to quantum sensors. So what makes quantum computers really hard today is that your qubit device itself is really, really sensitive to its environment. And that's a problem in quantum computers. It's called decoherence, and where it loses its quantum state. Now, that could be a really great opportunity as a sensor. You want a sensor that's highly sensitive to its environment. And this is where we see quantum sensors today trying to, that are already doing actually some really good work. Think of atomic clocks, actually. Those are the first ones. They're quantum sensors. That's how our planes get flown today. And other quantum sensors that I'm seeing getting developed are for radiometers, for example. So that's for gravity detection. Magnetometers, for example, that's for magnetic detection. And in fact, one example I can give you, so my day job is with the US government's organization called ARPA-I. If you know DARPA, ARPA-I is the ARPA equivalent for the Department of Transportation. And there is something we're exploring is the application of quantum sensors to help us with navigation. So imagine if you have a loss of GPS, or you have GPS jamming or spoofing, well, how else do you know with precision or somewhat precision where your vessel is? And of course, navigation has a rich history of, like doing celestial navigation and finding all these other ways for navigation. One thing we're exploring is magnetic navigation, so MagNav. And this is something that the NGA as well, National Geospatial Intelligence Agency, has taken up as well, where there's an effort now to map magnetic fields, especially for flight travel. And for our case, this is for maritime. Well, how can we then navigate a ship picking up the magnetic field from the ocean if we have the magnetic fields mapped out already? Some of the theoretical accuracies there we'll see is about 300 meters, which I think is sufficient. Within 300 meters, you also have visibility then, so line of sight, and that helps you then navigate. But if you have no GPS access, how do you find out your coordinates? Well, you could have 300-meter accuracy if you have a magnetic or gravimeter device on you.
There's also a report for folks to take a look at. The last administration's Department of Transportation did a quantum workshop that looked at quantum sensing and compute and actually identified a whole host. I think it was almost like 12 or 13 different use cases, both in the transportation and sensing side of things for compute and quantum sensing. So I highly recommend folks look at that report, because that was actually enlightening to see all the different use cases in both.
Yeah, and Allison was a fantastic panelist. I certainly recommend that as an organization as well, to bring the quantum experts and bring your users together and figure out where are these use cases and build a matrix of where can we find the highest value in quantum.
So we mentioned a couple of different things, right? We mentioned quantum sensing, excuse me, we mentioned quantum annealing, we mentioned quantum computing using gates, right, qubits, right? So let's talk about maturity, because you made the comment that if someone thinks quantum computing is going to be here 3, 4, 5, 20 years is unclear, and you counted, well, we have quantum annealing now, right? So let's talk about maturity, and let's talk about what some of the differences are in these things.
Yeah, so NIST has not done, well, nobody has really done a true objective TRL level assessment. There is one from NIST from June of 2021 that looked at kind of when do you need to do standards, and they did a very high level kind of TRL level assessment of the different quantum technologies. Quantum annealer's maturity level was a TRL level of 8. And a lot of that is because we have it commercially deployed, we have it forwardly deployed, we have applications that we're building. The gate model systems, there are two different types. There's the NISC, Noisy Intermediate Scale Quantum. That is really noisy, qubits pop out of their magical state, how do we fix it? And that is, those areas are kind of in the TRL level of 4 or 5. But there is a concern that you're never going to be able to scale those systems. The errors are going to get too great. When you have an error, you get no answer at all. So you actually have to go for error detection and correction versus error mitigation. And those, according to NIST at that time, again, 2021, that they were looking at those at a TR level of a 1 or a 2. I do policy, so I'm actually urging Congress and the National Quantum Initiative Act to have NIST do true TRL level assessments and keep those updated because this is advancing so quickly. I've been with the company now over 5 years. When I started, we just put one of our systems, our newest system in the cloud. Since then, we've had multiple hybrid solvers, another system come in the cloud. Other companies have advanced their technologies. This is the company we just bought, is the first post-NISC quantum gate model system. So it's not about correcting the errors, it's about detecting them and mitigating them right then in their dual rail technology. So there are different stages, and we really do need an objective readiness level assessment.
Yeah, if I can add, DARPA is doing a quantum benchmarking initiative right now. This is now a tiered and phased approach, but they're really testing different quantum companies and their computers.
But only gate model systems
as well as applications. Yeah, it's limited, but it's a resource one could use as well.
And then what about quantum sensing? What's the maturity of quantum sensing?
Yeah, that's a great question. So quantum sensors, that's what gets me really excited. I think quantum sensors are ready to come out of university. And certainly I see a role for us now as prospective users to start helping the academic community in our country to help bring these technologies out of the lab. Typically what I'm seeing now, a lot of them are falling through this valley of death where they're at TRL level 3, 4, and they start need to be doing early pilots. So I certainly encourage everyone else here to have a look at quantum sensors. Again, there are a variety of different quantum sensors. Something that I see that excite me, for example, are vapor cell clocks. So right now we have atomic clocks. Again, that's a type of quantum clock. There is now some work at NIST Boulder that's happening that's looking at, well, can we make that at a vapor cell level? Which should be exciting. It opens up a lot of applications.
I'm sorry, so why is that important? Why is the atomic clock important?
Yes, so quantum sensors, over classical sensors, they can be fantastic because of their sensitivities. Like I said, a qubit device itself or anything in an atom in a quantum state can be very, very sensitive to its environment. Now, can we tap that sensitivity because it knows its environment so well? Can we have that then, have it tell us, well, what is that environment looking like? And quantum magnetometers, for example, we are seeing them push boundaries at like nanotesla, picotesla levels. They can be very small, they have no drift, they don't need cooling. Some of them, like the magnetic, one example is the nitrogen vacancy diamond magnetometer. So this is where work done at Harvard University starting 2008, where they literally took a diamond. So a diamond is all carbon, carbon, carbon. You remove some of the carbon atoms and instead place a nitrogen and a vacancy in where a carbon atom may have been. So you change the bond structure a little bit. But then when you hit it with a 532 nanometer, a green light, it shines out a fluorescence light over to you, and that can tell you a magnetic field. The reason I tell you all of this physics behind it is it's very exciting because it's very stable. Some of the magnetometers we have today, the classical ones, they need cooling. Some of them need cooling, or some of them have high drift, or some of them don't have sensitivities. With the quantum one, again, they open up amazing applications for you.
I think the biggest thing to take away from what Prachi has just said is when we say quantum, everybody thinks it's one monolithic thing, and it's not. There are tons of different technologies under sensing. There are multiple different technologies under compute. Each of them have different use cases. Each of them have different strengths. And the issue really is to come to the table and say, this is my problem. is quantum able to solve it? And then we can come in and say, nope, quantum's not right for that problem. Yes, quantum can help with some of that problem, not all of it. Not everybody needs to be a quantum physicist, and we don't expect that. I mean, I look at my phone and I don't know how it works. I just know when it does and I know when it doesn't. And so quantum can be the same way.
So if I'm in TSA, let's say, and I need to schedule my agents, what would I do? How would I come to you? And then after I came to you, what would I do after that?
Yeah, so obviously that TSA scheduling application that we built with a large system integrator was pulling and ingesting all the different information and all the different components and the constraints. It's those constraints that make it so complex. And then we can run those scenarios multiple times. The speed in which quantum can compute cannot be the same as classical. We can look at a lot of different things in a nonlinear fashion, do it faster, and provide an answer. Sometimes it's the same answer, just faster. Sometimes it's a better answer. And so being able to look at it, so you come to us, we kind of understand your problem. If we are not the best person, we bring in a partner. So that's why for the government contracting folks in the audience, we do work with partners in order to understand kind of the mission sets that you all are experts in. And we train either you to develop that algorithm, or we help with our professional services team develop it with you. And we can start small, you know, one airport and then multiple or regional airports and navigate through that. You know, one of the things when it comes to speed, there is a missile defense application that one of our partners helped create down in Huntsville, Alabama, and it looked at a notional multiple ballistic missile attack in Hawaii. It looked at 67 million scenarios and provided an answer back in 13 seconds. That's the power of quantum. And there are some problems that you don't need that speed for a solution. There are some problems you have to have a faster speed to solution. So it really is kind of understanding your problem set, when do you need an answer by, and if quantum can help.
So how am I interfacing with this? I mean, you described a huge machine with cooling and all this stuff. How do I interface with it?
Cloud.
Cloud, okay.
Yep.
Okay.
It's not, there's not going to be, Prachi always says we're not going to have quantum in our, you know,
Our
laptops and phones, but you can access it. So yeah, I mean, there's AWS Braket, Google has a cloud platform, D-Wave has their own Leap quantum cloud service. You navigate through. One of my colleagues was actually submitting quantum problem sets while she was on a train in Europe and got answers back. So you know, it is accessible. It's not going to be on the edge. You're not going to put a quantum computer on the edge, but we can actually provide solutions cloud-based.
And what's the software? Talk about the software. Like what
So ours is our own proprietary software.
Yeah.
And so, and we work with our partners in developing that. But for us and our technology, we have a training program. And if you know how to code in Python, you can learn how to code for us. And we have online courses, we do in-person courses. A retail grocer came to us in Western Canada, and they had a staff scheduling problem. And we sat hand in hand with them and built that staff scheduling application with them. They came back to us with an e-commerce delivery solution and said, we believe that we learned how to do this. Could you help tweak it? So we built it with them the first time, they built their other one. So it's really not that difficult as long as you have folks that know how to code in Python.
And let's go back to quantum sensing. So you're excited about the magnetic sensing, right? So is that being used right now?
It's being explored for testing
and
pilots. Yes, the quantum sensors, again, sensors do different things. Pressure, some are sensitive to pressure, and they can tell you what pressure is, temperature, gravity, like I mentioned, time, and various other physical constants. So that's where I think different technologies are. I would say quantum sensors are a lot more mature than quantum computers. If you do want to get started on a quantum journey today, start looking at where quantum sensors can help you. There's another quantum sensor that's fantastic for radioactive material detection. Again, that has DHS applications. Navigation is one where we've easily found ones. Think of, again, how do we all know time today? Time is because, you know, we sync with the atomic clocks in space. Imagine if we all had clocks that don't drift over time and that could tell us time. So even if we lose a connection at any time, we can even navigate ourselves because we don't need a clock to sync constantly, which is what we need today.
So if I'm somewhere where I don't have infrastructure support, right? How would I use this? Like, where would I get this quantum sensor from, and how would I use it?
Yeah, plenty of companies in the US today here, as well as academic groups that are looking at quantum sensing as well. There are certainly hubs. There's a group called Quantum Economic Development Consortium, QEDC. It's run and it's supported through a White House initiative, and I think, I'm not sure exactly the mechanism, but it's a national consortium, and certainly their members are someone wants to look at.
It was created as part of the National Quantum Initiative Act that passed in 2018, funded by NIST.
Right, and was reauthorized recently as well.
No, it hasn't been reauthorized.
Okay.
It expired in September of 2023, and Congress just works so slowly, but the reauthorization bill has been introduced in the Senate, and the House is having a hearing today, and hopefully we can get it done this Congress.
Okay.
Prachi, another area that you...
The speed of Congress.
Prachi, another area of interest of yours is education.
Yes.
Right? So tell me, how are you thinking about education in this area?
Yeah, two things for education. It's not only bringing people into quantum or pivoting people into quantum, it's also making decision makers aware of how quantum can impact them. And I think conversations like this are really important, where, what does quantum mean for all of us? And for me, it meant like watching a bunch of videos, understanding what quantum meant. I come from the transportation background, and then putting a workshop together, really inviting the quantum community and the ecosystem and agency I work in, and saying like, let's talk and let's figure out what is the application. But I think, quantum education is something we'll all have to do. It's a bit like cloud education. I think we all learned how to deploy things on the cloud, how to move. I was hearing lift and shift earlier. We had to all learn this language, and I think it's just part of modernization. It's also part of national security. How do we keep ourselves abreast of quantum and understanding, I think, basic technology and terminology, like what does quantum key distribution mean? How can quantum computers be hacked? Well, how can quantum hack classical computers? All of that, I think, is going to become a question very soon. And the better and faster prepared we are, I think the better we will be as a country as well.
So one of the things, you just brought up hacking and all that. So Allison, do you want to talk about some of the quantum encryption and some of the challenges there?
Sure. Let me just go back a little bit on the training side, because I see training as twofold, and then I'll get to the encryption. Yeah. Training is twofold. One is knowing what quantum is good for. And that is, you can spend so much time and money and realize that you were actually running down the wrong path. So understanding what quantum is good for is important. Then understanding how to develop applications and develop the codes that you need for it from a computer, which sensing device. So think of training and upskilling as two different types of mindsets. One is making sure you understand what is ML best for, or AI, or HPC, or quantum, from the compute perspective, and then how do I actually get my workforce actually able to develop in this? So from a workforce development, think of it from those two mindsets. From the encryption perspective, I will say I agree with Prachi in the timeline. So the current RSA encryption is not in any danger of being broken by a quantum computer anytime in the near term. There are work that NIST is doing on post-quantum cryptography. Most of that work is actually classical solutions in order to break a quantum computer once it theoretically can break it. Google did a study years ago. We mentioned different types of qubits, and it would take, I think it was something like 20 million superconducting qubits to all work together to break a current RSA. I think we have 1,000 qubits in the gate system that don't all work together. So we are well away from the 20 million. And in photonics and ion traps, you need billions of qubits, and you're at like 64, 67, a couple hundred. So again, we have many, many more years. But understanding your data, making sure it is behind post-quantum cryptography, starting to morph it. It takes forever for those in the government, in the audience. It takes a long time for governments to move. And so you do have to kind of start that work. And I know that there's already work there today. And then for those supporting the government in the audience, you're going to be mandated to do it. So navigating that post-quantum cryptography is going to be important. And sometimes it could be a quantum solution like quantum key distribution. Other times it will just be a classical solution like the post-quantum cryptography that NIST is working on.
So there's a lot of things we still need to talk about here. One is, well, actually the session after this is on AI, right? Mm-hmm. So how does quantum interact with AI? Are there some advantages for quantum for AI? The synergies there?
Yeah, so I was really excited with the Genesis mission announcement because it really kind of, for the first time, theoretically broke down the silos in government.
Explain what the Genesis.
Oh yeah, so Genesis mission, it was part of an announcement that the White House put out. It includes kind of all emerging technologies from fusion to quantum to AI and others. And it actually reorganized some areas, like you now have a quantum and AI office within Department of Energy. And so everybody is kind of running at the same path. And usually the quantum programs were siloed off from AI. And that is actually now how it's going to be implemented. I mentioned a little bit earlier in the panel that we have done some optimization of some modeling of LLMs. This was in a drug discovery area, and we were able to actually cut the time and the amount of energy consumption used and get a better model for this drug discovery. It was a pharmaceutical division of a Japanese company that was doing the drug discovery. We're also doing it for agentic AI with a Canadian national lab, as well as with Jülich Supercomputing Center in Germany. So there is going to be a synergy with this. AI has some amazing capabilities. Quantum, especially from the compute perspective, is just that complex compute portion of it. So again, you're going to need both of these. You're going to have your staff trained up on them and understand, as you're building out a staff that knows how to code on AI and ML, get them learning how to code on quantum now. There's so many people who are doing it, and unfortunately, if you don't start learning now, you're kind of almost already behind.
Prachi.
Yeah, I'm very proud to say at Visor, we have one of the largest quantum machine learning experiments deployed on IBM computers today. And that is with a partner called E.ON, which is one of the largest grid companies and grid operators in Europe. And there we're looking at a time series forecasting using real-world energy grid data coming into the systems and then doing the forecasting with it. Something else we're doing is also a lot of benchmarking work. So our quantum algorithms, how do they compare to the classical ones? And if you run the same algorithms again on HPCs, high performance compute, what are the results? So again, I think Allison mentioned this earlier, not every problem is a quantum problem. Some things can be solved using classical computers, and that's what they're really, really fantastic for. Use them. Same with HPCs, use them. One example I would like to give is where we're seeing the really value of quantum, and earlier examples is anything with material science. And I'm curious here, any of you may be looking at materials. One of the partners for Visor is the US Naval Nuclear Lab. And if you think of the US Naval Nuclear Lab, they build the nuclear part of our nuclear submarines. And other things they're looking at within the submarine and the nuclear part itself are things like coatings and alloys outside the submarine. That's one of the hardest problems, right? How do you prevent rust? How do you prevent barnacles from sticking to your submarines? And this is again where material science is really, really important. Or think of corrosion as well, corrosion modeling. Actually, it's a really good quantum problem to have for quantum computers to solve. So start thinking of what are the kind of problems where quantum is really good at. And I think that's a great way to get started on that journey.
Yeah, and I think as you're looking at kind of where Prachi was talking about, from those problem sets, part of those are good for quantum annealers, part of those are needed for gate model systems. And so understanding, again, the capabilities of both. So, D-Wave did a quantum supremacy with Oak Ridge where we solved a quantum magnetic material simulation problem. We solved it in 20 minutes using $1 worth of energy. It would, at Oak Ridge, would have been up to 1 million years to solve the same problem with the entire annual cost of energy. So from an AI perspective, it's that energy modeling that's happening with it, but the quantum chemistry side, so we've done the material simulation, now we have to develop it and use a quantum chemistry. You're gonna need a gate model system for that. But what we did on that supremacy side, we actually realized we can do quantum proof of work in hashing for blockchain. And that's a new research area. So like as you're looking at it, these new applications are coming out. Again, I've been with the company 5 years. I was never even thinking my history in fintech with blockchain was ever gonna port into quantum, but here it is. So it is an emerging field, and so there's so much more happening.
Another example I think the audience would like is also some of the work you did with ports and optimizing port operations.
Yeah, we worked with a customer and they optimized cargo pier at the Port of Los Angeles, increasing truck turnaround time by 12%, increasing cargo per crane by 60%. And so again, they built it actually as a digital twin and then looked at every single thing that they could possibly do, optimize it, change the entire method of the port, and then in production did a pilot where, because they used to do first in, first out, a truck showed up, you found their cargo, you loaded it, you left. Now, because trucks come early, they come late, things were happening, they actually could pull out the trucks that showed up based on where the cargo was. So being able to optimize that port logistics, but think of that could be done at a submarine, that could be done at a military base, that could be done, for optimization of of maintaining DHS fleets. I mean, there's a variety of these different applications that could be used.
Let me see if you guys agree with this, and please push back if you don't. When I think about what kind of problems are best solved with quantum systems, it's combinatoric kind of problems, right? And this is because of superposition property that you brought up earlier, right? And annealing is a particular type of optimization problem. And so if you can put your problem statement in the annealing equation, that optimization equation, you can then use that method. If you need another type of optimization, maybe you need a gate model, right? Do you agree with that? Or
no, not fully.
Okay.
So the research has shown that optimization is probably always going to be best on an annealer, but quantum chemistry, differential equations, you're going to need the gate model system.
Okay.
It's a linear algebraic things where factoring sits and all that, either one, and we're not sure because we can't benchmark between them.
Okay.
So that's kind of it. For me, the question to ask as the non-technical audience is, you look at it and say, is your solution not good enough now? Does it come too slow? Can I not get the right solution? Can I figure out a better way to do this? And sometimes, we can shave off 5%, 10%, but that's millions of dollars and multi-millions of dollars. In Tokyo, we did an optimization of waste collection. We were able to collect waste, reduce the amount of trucks on the road. We were able to reduce the CO2 emissions by 60% by not having as much trucks. If we looked at one area of, let's say, CBP, and we're able to do the same operations but do it more efficiently, using less trucks, how much money would that save the American taxpayer? How much money would that be able to be redeployed for something else that's critically mission sensitive? So sometimes it's about, is there a problem that's outside the scope? Sometimes it's, I need a better solution faster. Sometimes it's, can I just find a way to save a little bit of money and redeploy it to something else?
Excellent. Thank you, guys. I think we had to go to questions from the audience. Any questions? Any questions?
You got a free quantum computer.
I'll tell you what, there's no questions right now. I do have another question.
Sure.
Something we talked about yesterday, research. Mm-hmm. So where do you think the next phase of quantum is going? Where do we need to look?
Prachi, you want to take that?
Yeah, I think simply put is implementation and getting better and better. So quantum for a long time was very theoretical. We needed physicists to help understand it and then it was very much lab-based. Now we are able to have larger qubit devices, and we have more and more engineers coming to the space. So I think this is where we are doing, companies like Quantum are building extensively in terms of the infrastructure itself. They have facilities, I think, at least in 4 locations. So I think quantum is nearer and nearer than you think. It's going from, again, science to engineering, and hopefully soon to a productization.
For me, I think that the future is identification of those applications. So you had Undersecretary Emil Michael identify 6 critical technology areas: contested logistics, AI, quantum. But quantum can help with a lot of those things, like AI we've talked about, and like contested logistics, it's a big optimization problem. You had Secretary Driscoll of the Army talking about quantum for transportation. You had the CTO of the Navy talking about quantum for logistics. I think a lot of those are going to be hybrid. So I do think the near-term future is going to be this huge opening up of quantum applications. The Inspector General actually at Department of War just released a report saying that the department failed to follow fiscal year 21 NDAA that said find the problems in 1 to 3 years that you can solve with quantum and provide an annual report. They basically said in the beginning we can't do anything and then never looked at those applications. So I think the near term is really going to be that robust idea of what can the Army do, what can the Navy do, what can the Coast Guard do, what are the different components at DHS and those applications. That's kind of the near term excitement while the companies are figuring out how to scale.
So there's a chicken and egg problem, isn't there? Because if people don't know this that well, right, they're not going to come to you with kind of problems. So how do we fix that? How do we help that?
I think through CRADAs, I think through prototyping. D-Wave is the only quantum system that I know of that's on the TradeWinds marketplace platform.
Okay.
So we can build prototypes and navigate through that. And, you know, frankly, you have allies that are leaning in on applications where the US was focusing more on the hardware. And so for me, that's kind of where it is. But it really is just rolling up your sleeves. And the minute you have one success, everybody else is going to say, oh, wait, I didn't realize we could do this. We should come over here. And because it's cloud-based, it can actually be integrated into one pane of glass.
Got it.
Yeah, maybe I'll just add
Good.
in terms of applications, reach out to me, reach out to Wiser. I think organizations like ours, there are a couple of other research organizations that help and build applications. Again, you want to understand how do I even get started with quantum. And initially, it is that prototyping, it is that piloting, maybe having 6-month, 12-month research projects in different areas, understanding, well, where does quantum really give me an edge? Where does it not give me an edge? Can I try one of these hard problems I have on a quantum computer today, test it, and see, well, is this something I want to spend and put in more R&D money into? But the first step is always asking, well, how do I even get started? And you know, same with Vanguard, we're actually starting with 3 research domains for them. And then as they understand the value of quantum, then we expand from that side.
Great. So that's the last word. I want to thank our great panelists.